So now that we've talked a bit about power series and Maclaurin series, let's start addressing that question of when does the series actually equal the function, right? So, for a simple example, right, one we talked about before was this function 1 over 1 minus x. And we used recognizing this as the sum of a geometric series to write it as this series here. Right, but then we said this is only valid for absolute value of x less than 1, or in other words, on the interval from -1 to 1. Right? But, we can say over here that this series, or this function, this is valid for things outside of this interval. In fact, only at x equals 1 is it undefined. Right? So, how do we figure out this process if we have something more general? Like, for example, we did in the last video that sine of x is equal to this sum, -1 to the k, x to the k over, 2k plus 1 here. And divided by 2k plus 1 factorial, right? For what interval is this valid? Is it valid only on some interval around 0? Some small one? Is it valid on everything? How do we do that? How do we find these things out? All right. So this is where the radius of convergence comes in. So let me start off with sort of a visual idea of what the radius of convergence is for a function. Right? And I'm going to use this as an example up here. Right? So let's see. We'll be looking at this. So if this is x equals 1, then our function 1 over 1 minus x, let's see, 1 over 1 minus x will look like this. Here. Did I get that right? Let's see, when x is 1, when x is 2, it's -1. Yeah, I think I got that right. All right. So what's going on here is this series up here, this is centered at x equals 0. So the center of the series is this green line right here. And what the radius of convergence is saying is sort of from this line, if we move away from it, how far can we go before one direction or the other hits like a discontinuity or something in the function? And as it would turn out, it's, well, we can go all the way up until we hit that line. So we can move a distance of 1. And so we're actually only allowed to move a distance of 1 in this direction as well. And that corresponds here to the interval from -1 to 1, right? And that's sort of visually what the radius of convergence is saying. It's saying that, all right, here's the center of your series, right? Here we have x equals 0. And the reason it's called a radius is we're only allowed to move the same amount in both directions. So we find the furthest we can move out to the right, the furthest we can move out to the left, take the smaller of those two numbers, and that's how far we're allowed to move overall from x equals 0. Right? That's sort of why it's called a radius here. And you can almost imagine it's like if you draw a circle of radius, in this case 1, centered here, it's going to hit at these 2 points. Right? That's sort of the idea. And in fact, radius makes more sense when we talk about, say, power series in 2 variables. All right? So how do we go about actually computing this stuff? Well, so let's write down, actually, let's pull up Mathematica real quick. I have some nice text here that is easier to just read instead of writing the whole thing. We get the right thing. We are getting the right thing. Awesome. So here's a theorem. So this actually applies no matter where the power series is centered, right? It can be centered at 0. It can be centered at A. It doesn't actually matter. All right? So there's 3 things that can happen. We can have the series converge absolutely no matter what the value of x is. All right? In this case, the radius of convergence is is infinity. Okay? So we'll see some series that behave like that. Another way it can converge is if there's some real number that the series converges absolutely in this interval here. So this corresponds to the interval a minus r to a plus r, right? And it diverges outside of that. Now the question is, well, what goes on at the endpoints? Well, remember we talked about alternating series test, integral test, all that good stuff. We do that because that's how we test the endpoints here, right? We can't actually do that independent, or we can't fold that into this. We have to test the endpoints independently, right? And the other thing that can happen is you have a radius of convergence 0, which means that the power series converges only at the center, right? And actually, in that case, it's not a very interesting power series at all, right? But it's worth knowing, if you have a function and its radius of convergence at a certain point is 0, you're not really going to be able to sort of expand at that point, right? So let's look at some examples here. All right. So let's start with the series. Let's start with the series k equals 0 to infinity, x to the k over k factorial. Right? So hopefully you recognize this series, right? This is the power series, the Maclaurin series even, for e to the x. Right? This is a quite important series, this one. Right? I strongly recommend trying to remember this one. All right. So let's find the radius of convergence. All right? Here's how we do this. To find the radius, we're going to use the ratio test. Right? So how do we do that? Well, we want to find out when does this thing converge, right? Here's what we do. So we're going to do our usual ak plus 1 over ak. So this will be x to the k plus 1 over k plus 1 factorial times 1 over ak. So this is just this. Right? So after simplifying all of this, we're going to get x over k plus 1. Okay? Now, for the radius of convergence here, right? So what we're going to do is say, all right, little r, this is the little r from the ratio test. This is limit as k goes to infinity of, absolute value of ak plus 1 over ak. Okay? And so let's plug in what we get. Right here, x presumably can be positive or negative. So we're going to leave that absolute value on the x and say, all right, well, this is over k plus 1. All right. So actually, we can leave off this little r equals. All right. So this limit here, okay, what we would really like in order for this to converge, remember, is we want this to be less than 1. So all x values which make this limit less than 1, the series will converge absolutely there. But now here, since x has nothing to do with k, this is just a constant over k plus 1. So this limit is 0, which is always less than 1. So if we do this limit and we get 0, what this means is that the radius of convergence, which we usually call capital R, is infinite. Because no matter what x value I put here, this always converges absolutely by the ratio test, right? And so the interval of convergence this is in fact just minus infinity to infinity, right? So this is really quite interesting here in that, no matter what x value we plug in, this series right here is going to converge to e to the x for every single value of x. It's quite interesting. All right, let's look at another example here. All right, we'll look at an example here for a series that's not centered at 0. All right, so sum from 0 to infinity, 2 to the k over x minus 3 to the k over k. All right, what's going to go on here? Well, we need to set up for the ratio test, so ak plus 1 over ak. Okay. So this is 2 to the k plus 1, x minus 3 to the k plus 1 over k plus 1 times k over 2 to the k, x minus 3 to the k. All right, simplify what we can here. And basically that's going to mean this stuff goes away and these k's go away. And we're going to have, really, let's write this as k over k plus 1 times x minus 3. All right, let's write it like that. You'll see that'll make things a little bit nicer. All right, so we have to compute this limit from the ratio test. All right, so absolute value of ak plus 1 over ak. This is the limit as k goes to infinity. Now again here, we have to take the absolute value of all this stuff. Well, this part, is always positive, so we don't need to bother. Here, we need to keep the absolute value. So this will be k over k plus 1, absolute value of x minus 3. Right? So that absolute value of x minus 3 has nothing to do with the limit for k. So really, you can factor it out like this, and then do the limit if you want, if it helps you sort out the limit here. But what you'll find is, all right, this is x minus 3 times 1. Right, this limit here is 1. And we want to make sure that this is less than 1. Right? So what we get then is this inequality has to be true in order to converge absolutely. This number right here, right? So here, once we have x minus the center, oops, I got that all messed up. Here we have x minus the center absolute value, right? No power here. This number right here is the radius, right? So the radius of convergence here is 1. All right. The interval of convergence, so here the center is 3. So we'll have 3 minus 1 and 3 plus 1. The question is, do we use parentheses or bracket here? Right? So, we'll have 2 to 4. And then we need to test at these endpoints, does the series converge there or does it diverge there? Right? What happens? So for x equals 2, right, we need to test both of these endpoints. So we take these values and we plug them into the series. Right? So plugging in x equals 2, we're going to get the series k equals 0 to infinity, 2 to the k, times 2 minus 3 to the k over k. Right? So if we simplify everything here, you're going to find that this is just negative 2 to the... Or sorry, let's not do it that way. This is negative 1 to the k, 2 to the k over k. Right, so you're going to find that we have this. And this series here, this is going to diverge by the divergence test. Right, and that's because, 2 to the k is going to grow much faster than k, so this limit isn't going to be 0. Right? Now we do the same thing at x equals 4. Okay? Plug in x equals 4, and we get 2 to the k, 4 minus 3 to the k over k. All right, so this series is simply the sum from 0 to infinity. This is going to be 1 to the kth power, which is just 1. So we're going to simply get this. But this also diverges by the divergence test. Right? So what that means here is the interval of convergence, it doesn't converge at either endpoint, so it's open parentheses. So the interval of convergence is the open interval from 2 to 4, right? It doesn't converge at either endpoint. However, if we were to plug in, say, one of the endpoints and get a series that does converge, then yes, absolutely, you would have, say, a half open interval. All right? So let's look at one more example to end this video. All right, it's that example that we know we've looked at already. This series from k equals 0 to infinity of x to the k. All right? So we've already talked about this one a bit. We know that the radius is 1, right? And this converges for absolute value of x less than 1. But the question is for the interval, the interval is from -1 to 1. Now, it will only converge absolutely on the open interval. The question is, does it converge at all at the endpoints? Let's check that. Well, when x equals 1, when x is 1, we get the series... Sorry. Am I doing something off here? No, we're good. Sorry, I want to look at a different series here. Not this one. Let's look at a slightly different series. This one does actually only converge on that open interval from -1 to 1. I want to look at a series x to the k over k. Right, something a little more interesting. Right, this was our series for ln of x, or ln of 1 minus x. Right, let's see, if we go back here, we can probably find this. Where did it go? Okay, this one here. Oh, so is, sorry, negative here. Right, so let's look at this series here. Right, So this is basically for ln of 1 minus x. I'm going to leave off the negative. It's not going to do anything interesting. So this series right here, this converges for x less than 1, absolute value of x less than 1, right? So the radius in this series is in fact 1. However, what about the endpoints of this? Well, since this is supposed to be for ln of, well, this is negative ln of 1 minus x, really, we would expect to maybe be able to plug in negative 1, but not 1. So let's try that out. Let's plug in x equals 1. Right, if we do that, we get the sum from 0 to infinity. This is just going to be of 1 over k. And we know this diverges. Right, this is the harmonic series. Right, so if you wanted to verify that, you would use the integral test. On the other hand, if we plug in negative 1, we get this series. This converges. This is the alternating harmonic series. Right, alternating harmonic series, which we showed by the alternating series test, actually does converge. So the interval of convergence is actually closed bracket 1, closed bracket negative 1 to 1 open bracket, right? So pretty interesting how this stuff can work out. So in the next video, we're going to talk about computing a sort of the analog of a Maclaurin series centered somewhere other than 0. And this is what we call a Taylor series.